In this segment, we'll talk about the least upper bound property of ordered sets. Here's a quick overview. We'll begin by defining relations in ordered sets, then introduce the least upper bound property, and then show that it's linked to what might be called the greatest lower bound property of ordered sets. We start with the definition of a Cartesian product. If you have two non-empty sets A and B, the Cartesian product of these sets is the set of all ordered pairs such that the first element is a member of A and the second is a member of B. And a relation R from A to B is just a subset of this Cartesian product. And we can write this in two equivalent ways. We can say that the ordered pair AB is an element of R, or we can write ARB. And if A and B happen to be the same set, if R is a relation from A to A, we say that it's a relation on A. An important property of relations is transitivity. We say that a relation R on a non-empty set is transitive if for any three elements of A, let's call them A, B, C, if the ordered pairs AB and BC are in R, then so is the ordered pair AC. A particular type of transitive relation is an order, which is defined as follows. An order is a transitive relation, which we're going to denote with the less than symbol, and it has the property that for any pair of elements x, y in a set S, either x is less than y is less than x, or x and y are the same element. And we use the notation x less than equal to y to indicate that either x is less than y or they are the same element. And an ordered set is just a set on which an order is defined. Now these definitions apply very naturally to sets of numbers, but the definitions are abstract and they can apply to any set. One example of an ordered set is the set of words in the English language, and you can think of this set being endowed with the alphabetical order, or the order in which these words appear in a dictionary. Another example is the set of rational numbers, which we're going to examine in more detail in a minute. Next, we introduce the concept of boundedness. Now, suppose S is an ordered set and E is a subset of S. If there exists an element Y in S such that all elements of E are less than or equal to Y, then we say that E is bounded above and Y is an upper bound for E. And lower bounds can be defined in the same way, using the notation greater than or equal to. Suppose S is an ordered set and E is a subset of S and it's bounded above. Suppose that the element Y in S is an upper bound for E, but no element X that's smaller than Y is an upper bound for E. Then Y is called the least upper bound or supremum of E. And we can define the greatest lower bound or infimum of a set in exactly the same way. An ordered set S is said to have the least upper bound property if every non-empty subset of S that's bounded above has a least upper bound in S. Here's an example. The set of rational numbers does not have the least upper bound property. Now, there obviously exist sets of rational numbers that are bounded above that do have a least upper bound. For example, the set of rational numbers less than 1. But there also exist sets of rational numbers that are bounded above that don't have a least upper bound. And so all we need to do is to identify one such set to show that the set of rational numbers does not have the least upper bound property. And you can do this by considering the set of rational numbers that are greater than 0 but whose square is less than 2, and use the fact that there exist no rational numbers whose square is equal to 2. And I leave as an exercise for you to show that this set does not have a least upper bound within the set of rational numbers. Now here's the main result we want to prove in this segment. If S is an ordered set with the least upper bound property, then every non-empty subset of S that's bounded from below has a greatest lower bound. In other words, if a set has the least upper bound property, it also has what might be called a greatest lower bound property. And I'll sketch out the proof with some missing steps that you should fill in. Now suppose S is an ordered set with the least upper bound property, and B is a subset of S that's non-empty and has a lower bound in S. And the goal is to show that B has a greatest lower bound in S. Let L denote the set of lower bounds for B in S. And this set is non-empty because B is bounded below, so L has at least one element. Now each element in B is an upper bound for L, and this follows just from the definition of L. If there were an element in B that was smaller than some element in L, then L couldn't be the set of lower bounds for B. Now since B is non-empty and every element of B is an upper bound for L, L has an upper bound in S. And we know that since S satisfies the least upper bound property, L must have a least upper bound in S, and we're going to call that Z. Now to complete the proof, we're going to show that Z is in fact the greatest lower bound for B. The first step is to show that it is a lower bound, so it's an element of L. To show this, consider any element Y that is smaller than Z. Now Y can't be an upper bound for L because Z is the least upper bound. And so Y can't be an element of B because every element of B is an upper bound for L, and Y is not an upper bound for L. So we conclude that any element Y less than Z cannot be an element of B, and therefore Z is a lower bound for B, and therefore Z is an element of L. To complete the proof, we just observe that for any element X larger than Z, X is not in L. Because if X were in L, then Z couldn't be an upper bound for L. Putting these two claims together, we see that Z is in fact the greatest lower bound for B. And this proves the result that if S is an ordered set with the least upper bound property, then every non-empty subset of S that's bounded from below has the greatest lower bound in S. And that's it for this segment.